is Vladimir Lazarev. I'm head of laboratory for stabilized laser systems from Bauman Moscow State Technical University, and I will speak about new types of laser systems. This is modern solid-state and old-fiber lasers in mid-infrared region, and I will speak about this technology and its possible and perspective applications. Okay. My name is Vladimir Lazarev. I'm from Bauman Moscow State Technical University. I am head of laboratory for stabilized laser systems, and we are developing several types of modern solid-state lasers. And I will speak about some laser technology that we have in our laboratory, and when electricity comes to us, мы можем, да, уже что-то запустить, нет? А чего, ноутбук не запускается? Ну давай, да, окей. Там у меня первая часть, and I would like to introduce outline of this day, and the first part of the lecture is a brief introduction about my university and about my center and about my laboratory. After that, we will do some experiments with lasers and optics, and these experiments are supported by the International Optical Society, OSA, and I am also as an ambassador of this International Optical Society. And all the equipment is produced by this society for student chapters. We have student chapter in our university, and the main aim of these chapters is to teach optics to youngsters, to children in different schools, and our students. Нужно, да, обязательно? Или вы звук же сюда пишете? Может быть, это не нужно, зачем нам? Да, мне кажется, слышно с первого ряда. Нет, я думаю, это лишнее. Окей, давайте выключим тогда на всякий. Ну, можно открыть, то есть это папка РНФ и... А что с экраном у нас? Лазарев. Ломоносов 2019, вот. Подглядела, все подглядела. Мне стабильность не дали, не волнуйся. А вообще хорошо видно-то. This is the key phrase for this day. Don't mess with science, we have lasers. Is it clear for you to translate in Russia? Is it clear? No? Could you help with your colleague to translate? Don't mess with science, we have lasers. What does it mean? No, in Russian, could you translate? Что это такое по-русски? Скажите. Ну, это просто забавное слово. Мне кажется, по вашей реакции вы не поняли шутку пока еще. Поняли? Ну, скажите по-русски, что это значит. Месс — это не заигрывай с наукой или... Не связывайся с наукой, да. У нас есть лазеры, мы всех стреляем. И my name is Vladimir Lazarev, this is Sergey Tomilov, and the next slide. We have clicker. Outline of this day. The first, what is laser? Then we will do experiment number 1 with some optics. The topic of the lecture is with modern solid-state lasers in mid-infrared region, and I will explain to you why mid-infrared region is important. After that, I will talk about our secret laser weapons that we are producing with our colleagues, our Italian mafia colleagues, we have collaboration with Politecnico di Milano and with German mafia. And after that, I will talk about fiber weapon, solid state weapon, and briefly describe perspective applications of our lasers. And after that, we will carry out experiment number 2 and some kind of, instead of conclusion. Next one. Who are we? We came from Bauman Moscow State Technical University. This is the oldest technical university in Russia, founded in 1830. Our Center for Photonics and Infrared Technology was opened by the former Russian President Dmitry Medvedev in 2012. And my lab is the youngest lab in our center. Was opened in 2017, simultaneously with the presidential program in Russian Science Foundation. This program was started in 2017, and my research in this lab was supported by this program, presidential program. And this is the best team in the world. Next. And our main directions of our research and our collaborators, I just briefly explained to you. The first direction is frequency stabilized lasers, and this direction is in strong collaboration with Lebedev Physical Institute of the Russian Academy of Sciences. The next one is erbium doped and thulium doped fiber lasers, and we have collaboration with Fiber Optics Research Center, Bihang University in Beijing in China, and Max Planck Institute for the Science of Light. The third direction is mid-infrared lasers, and we have strong collaboration with Italian Mafia, Politecnico di Milano, and Lebedev Physical Institute as well. The next one, and our main technology is broadband anti-reflection microstructures for laser crystals and windows that we produce in collaboration with Institute of Solid State Physics in Moscow region. And the next slide, we are focused on mid-infrared lasers. But I talk laser, a lot of word laser, but what is laser? What does it mean? The next. And my colleague Sergey tried to answer to this question to you with the help of some experiments and some experimental models that we are bringing to you.
First of all, we should start from the glasses, right?
No, magic glasses, and after that spectrometer. Yeah, we have special magic glasses to you. Excuse me, are you an organizer or just... you could sit here just to make our group compact, yeah, because we have some experiments and some.
Does anyone need some more glasses? Or?
Так, у нас уже.
Is anyone equipped? Yes. Okay, that's great. Please. What are we going to show first?
To show the difference between order light source and between light source and laser source, and with the help of these glasses.
Would you be so kind to put your eyes up to the lamps and describe what you see? What do you see?
Like rainbow.
Some kind of rainbow, right? but this is not a model rainbow.
Going back to physics course.
No, if we just ignore the physics and remember what the typical rainbow looks like. They're all colors which compose the white light, right? But I may guess. Let me see this too. No, this lamp is very good.
No, we can use this sources.
Not really.
Yeah. No, you can just go to. We have some lamps and whatever. This is laser, and this is just lamps, green, blue, and red. And if you will look through this whole, if you see to this light source, you can see a spectrum. Colors consist of this light, and you can observe that it's not just red, but a lot of other lines. Which colors do you see in this?
Orange. No.
Что-нибудь видно? Я давай сам смотрю.
So you're looking just at the left.
No, you can observe the red point in the center, and on the right hand and left hand you can see a spot with different colors. Could you? And we have we need to click some slide to answer this. So this one is blue, but in these 2 points you can observe different colors. Could you? And this is green source. So this source is not a laser because it consists of different colors. So the main feature of laser source is monochromatic, so just one color. If we see through this super glasses on the laser source, we just will see what we will see when we will observe the laser point. A lot of colors or just one color? Just one. So this is laser, and I need just a piece of paper. And you can observe this point and these 2 points on the left and right hand side, and you can observe just red color, no other orange or green. Could you see this point? Yes. So could you just explain this picture, maybe?
This picture, okay. Well, right now all of you observed some kind of beautiful or not so beautiful effects with our glasses, but we are scientists. We are boring people who trying to implement technically everything that we could see. And what is these glasses? Just a thin film with very narrow, very small lines in it. And when the lights interact with this thin film, with the lines in it, we can see that it turning into the spectrum. Like
each color goes to each angle, different angle, and you could observe in a central point red or green or blue point, but in the first or minus first order, you can observe a spectrum of this source. This is the difference between laser sources and just ordinary sources we use in our experiments. And after that, we can use spectrometer. Yeah, and yes, the next slide is about that.
So the main idea is that we can use this kind of glasses or their analogs to gather some information about the light, about the spectrum of this light. So there is a compact spectrometer, the device that you see here. Schematic of this device is shown on this slide. The light that we want to analyze is being put into the spectrometer due to the hole 1. It transits by the system of mirrors 4 and 5 to the diffraction grating. This is exactly the same film that is in your glasses, but it works into the reflection, not the transmission of light. And when our lights are being diffracted, it spreads into angle. We catch it with the matrix of photodiodes. I think that all of you know how the photometrics work. There's elements in our cameras and the photos. Just the array of light-sensitive pixels, and we can right from this picture we can see that each pixel is corresponding to one color, which we obtained from our white light. So we can just take a signal, electric signal from the pixels, and determine, okay, we have this amount of red, this amount of green, this amount of blue, and so on. So let's
ты можешь переключить, пока я попробую объяснить вот эту штучку. Что еще раз?
Можно просто вернуть его к аудитории, мне кажется.
Кого?
Ну, комп.
Ну окей, давай так, да. In our first experiment, you have glasses and your own eye, but this is a device produced by based on the same principle. Instead of these glasses, we have diffraction grating numbers 6 and 5. And instead of human eye, we have a special photo detector. It consists of several parts. And we just have special program which can give us an information about the spectrum of the light source. So this is...
Here's the software. There is wavelengths in the x-axis. As I said, we are scientists, we're boring people, we're trying to explain anything in numbers, and the wavelength is a measure of color for us. For example, the red lights have a wavelength of 600 nanometers, green lights have a wavelength of 500 nanometers, and the green is a 400. So right now, we are going to put different light sources into these spectrometers and observe their spectra. So first of all, let me start from the ordinary lamp, just a white light. I'm not going to put it into your eyes. No tricks, just lamp. And
Can you see something on the screen? No. Да, okay.
So this is a spectra of the white light of the lamp, and this kind of spectra are being emitted of any substance that have some temperature larger than absolute zero. So anything that have a temperature, it glows. All I ask of you is to ignore this kind of strange modulation. It's just a mistake of software. We can see that, yes, it's really white light. We have a wide spectrum of any wavelength in the visual range.
Visible range.
Visible range. So, do we have some color? filters?
We have this one. Maybe we can
Could you
use
repeat, please, what is the measure of the horizontal
axis,
It is a
horizontal axis.
color or just a wavelength, yes.
Yeah.
And the y-axis is the intensity of light. So let me just, maybe we can start from the smartphone screen.
No, okay, it's just up to you.
Just say something to our listeners.
So we just ordinary light source have very broad spectrum, and this no, I just try to. This source is quite small, have quite smaller bandwidths, but it's just too high. This is blue source, and the wavelength range is about 400 nanometers. This scale is measured in nanometers. This is wavelengths of light, and this is red part of the visible spectrum, and this is green part. Green part is the center of visible range. This is green source. And when we use laser source, I can try. Yeah, you can see very thin line. So the spectrum of laser is very the width of the spectrum is quite small. So this is the main distinctive feature of a laser, and we just can.
A few words about spectrum analysis.
Yeah, a few words about spectrum analysis.
So okay. Right now I'm going to insert this kind of light into the spectrometer. What will I see? How do you think? Which colors? What colors?
You mean
Okay. Wavelengths or no? We just can operate with colors.
Okay. Maybe somewhere near red,
And
and so it should be pink. So it's maybe somewhere.
And maybe this is some mixture of colors, red and what is your just an idea?
okay,
No,
let's
we
try.
can
We have a
try to.
hypothesis. And we see red and blue colors. And the next level.
And the blue would be more intense because it has a higher peak.
I don't think. I think that it's because of this color. This amount of red and blue compose the color I showed for you. And another color, the white again. What I'm going to see?
Full spectrum.
Whole spectrum, like the lamp, right? Let's try this. I have a question. Where is cyan? Where is infrared? And where is yellow?
Maybe it depends that on the screen of your smartphone they use 3 pixels.
Absolutely correct. The screen of my phone is composed of 3 types of pixels: only blue, only red, and only
Can show.
green. It's not heat stars, which composed of any wavelengths. So using this kind of devices, we can analyze the spectrum of light and make some assumptions and hypotheses about the light source. We can analyze the star radiation and think about and analyze the spectral and the chemical composition and anything like this. So right now we just analyze it 2 light sources, the lamp and the smartphone screen, and made some conclusions about them. There is a difference. And this is a basics of the spectroscopy of a science discipline which allows us to inspect any light sources by their spectrum, emission spectrum. And here is a display of the smartphone under the microscope. So I think it's all about the spectrum.
Okay, and the next slide is about the structure of laser source, and laser. Do you know the word laser? This is an acronym produced by this sentence: light amplification by stimulated emission of radiation. And laser sources consists of two mirrors. Output coupler and one mirror and output coupler and active medium, and these three elements. The laser is just this three components. Laser cavity consists of two mirrors and active medium. And what we do in our lab, because the first laser was produced in which year? How do you think? When was opened and when was designed the first laser in the world? When? 100 years ago, 50 years ago, approximately. What do you think? No. Yeah, in 1960, the first laser was produced by Theodore Maiman in the United States, and since that time, scientists all over the world would like to want to cover all the spectrum, including visible range, infrared range, all the spectrum with new types of laser sources. And oops. Can we just skip it? Что-то можем мы? Okay. The next slide. Why mid-infrared region? Because in our laboratory we are focused on the development of new laser systems in middle infrared range. This range is invisible to human eye. I can get you a very secret information, because visible range is quite short range in the whole spectrum of electromagnetic radiation. And for example, visible range, could you show when on this scale the visible range is? Where? Could you just show to
Using
the audience? Yes.
Things. Something like.
Yeah. This is a visible range, so we can see green, red, blue in this region, but a lot of radiation can cover this long spectrum from 2 to 14 microns. And why this range is important? Because a lot of molecules has distinctive features, absorption lines in this spectrum. And if we will produce some laser source for this region, we can move to some spectroscopy and develop new types of spectroscopy systems in mid-infrared range. And in our laboratory, we just cover a short part of this mid-infrared range. Could you show which part? Just from 2 to 3 micron, it's just our part of this huge amount of work. Just we try to cover this wavelength range from 2 to 3 microns with our lasers. And after that, we can switch to our laser crystals. So the main part of the laser is active medium, and our colleagues from Lebedev Physical Institute have special technology to produce new types of laser crystals, and on the basis of these crystals we can design new types of lasers. This is just maybe for chemicists. You're a chemist or chemicist? Just okay. No, it's just for chemists called coagenites and types of crystals. No, I can. We can skip it. The next, this is the technology of growth of these crystals, and after that, this is several types of the crystals, laser crystals, and in our setups, we just use these small pieces of crystals. And these crystals has a luminescence spectra from 2 to 3 microns. We are working in this region. We are working in this region, and we have several setups based on this crystal: zinc selenide doped by chromium and ions, and cadmium selenide doped by chromium ions. And after that, our secret weapons, but we have time just for 1 or 2 weapons. I keep other weapons in a secret. The first one with Italian mafia, we have secret laser weapon in collaboration with Politecnico di Milano, a well-known group in laser technology in the world in this university, Professor Svelta, and our PhD student came to this group and produced cadmium selenide doped by chromium laser with new type of crystal. This crystal was produced in Russia, and we just form a laser setup. This is an active medium. This is one mirror. This is dichroic mirror. Dichroic mirror needs to make the laser radiation tunable. So, for example, this laser in my hand is not tunable. This is just one color, and that's it. But our crystals have a possibility to produce broadband spectrum, and we can tune the wavelengths of our laser in a small region near 2 or 3 microns. And we tune our laser from 2 micron to 3.2 approximately micron. This is a tunability range of our laser sources. The next secret weapon we have in our Bauman University in Moscow. This is a schematic. We just have one mirror, our supercrystal in the cavity, and output mirror. And this is just for measuring some parameters of this laser. And what does look like, but just picture is not. This is in this region. This one. You can see a small crystal here. This is our laser crystal, cadmium selenide doped by chromium. And this heat sink was produced by Sergey. Maybe Sergey could say some words about this construction, just several words.
These crystals are very much influenced by heat, and their performance is strongly depends on the temperature of crystals. So right now we encounter some kind of limitations connected with the performance of our lasers, just because we cannot heat them as they want to be heated, to cool them more than they want to be cooled. So right now you can see the basic cooling setup, just a copper heatsink with a clump in crystal, which being cooled by the water flow.
This is water flow. Okay, just go next. And we have a world record on these types of lasers. 2.3 watts in continuous wave regime, under 6.2 watts of pump power. This power is quite big for laser systems, and Sergey could could say some stories about his arms and the laser beam in our setup.
These beams are invisible, and during composition and developing and building all these schematics, I frequently put my arms accidentally to the beam, to laser beam, and it causes like
Ожог, не знаю. Heat damage of the skin, burning. Yeah, thank you. Because this radiation is invisible, and when you случайно, occasionally, accidentally put your arm into the beam, you can just have damage. And also our results just in press in our new article, and Sergey is one of the author in Optics Express journal, well-known journal in this field. The next one. What difficulties we have with this crystal? The reflective index of this crystal is quite high, so we have quite high losses on the reflection. No, I can just briefly explain to you. When you observe just on this surface, you can see that part of radiation that goes through the lamp just reflected from the surface. This is a special reflective losses, which name is Fresnel losses. Maybe I can tell in Russian some. Ну, то есть, когда свет проходит через вот эту пластинку, часть излучения теряется за счет отражения от поверхности, и поэтому это называется френелевские потери. Вот, и чем больше, там, одна из характеристик этого материала, показатель преломления, тем выше эти потери. И для наших кристаллов они очень большие, потому что очень большой показатель преломления у кристаллов. And we need to make these losses smaller and to cover special anti-reflective coating on the surface. For example, in your eyes, I can see some anti-reflective coating. And some kind of coating we need to put on our crystals, but in your eyes you just get several milliwatts of radiation through these glasses, through this coating. But in our lasers we have watts of radiation, is quite high power. So we have some damage on these anti-reflective coatings. То есть, когда мы используем очки, у нас, ну, там проходит слабое излучение, и нас не интересует вопрос лучевой прочности, да? А у нас там ваты гуляют, которые там руки прожигают насквозь, и у нас образуется отверстие огромное, да, на этих покрытиях, они трескаются. And what is our decision is new technology of surface microstructuring. So we can produce a special microrelief on the surface of the crystal by special technology. And due to this microstructuring, we can make losses smaller, and the next slide will show us the next one. The next one, yeah. And we can observe that for our technology, this is a small points on the surface on the crystal. We have this crystal, and we have other type of laser, and just burn holes in on the surface of the crystal, and to produce this microstructuring. And for example, for 5.5 micron, we just obtain approximately 100% transparency. Yeah, this graph shows transparency of uncoated crystal, То есть черный график — это без покрытия, видите, 84% только пропускают. А когда мы делаем вот эти микроструктурки, мы выжигаем дырки на поверхности кристалла, мы получаем просветление, и видите, вот этот график показывает, что практически до 100% на какую-то из длин волн. So this technology is to produce anti-reflective coatings on our crystals. And we have, go back, just go back. We have, no, just one slide. No, just go forward. And we have some paper in Optical Materials Express, just, how to say, just in last month it was published in Optical Materials Express, these results. The next one. And I just have a couple of minutes to talk about some prospective applications of our lasers. As I said, and as you, I hope, understand, that our lasers are produced to laser radiation in 2 to 3 micron range. And for example, for 3 micron range, this is a very important point in the spectrum, because we have strong absorption lines for water and for collagen. Collagen is a special main building material for our skin, специальный белок. Skin, bones, teeth. Also, we have strong absorption lines in 3 micron for dentine, which is a part of our tooth, and some hydroxyapatite, I don't know in English how to say, which is in our bones. And we are thinking about medical applications of our lasers, and we started with our colleagues from Sklifosovsky Institute and Sechenov University. We just started some experiments to measure optical characteristics of biological tissues and its phantoms. In English, phantom, так и будет, наверное, фантом, да? To measure characteristics in optical in mid-infrared range, and the distinctive feature of our laser is tunability, and we can tune the wavelengths. We can put the wavelengths of the laser just on the center of this absorption line, and the penetration depth of radiation in that case is about 20 micrometers. But we can tune and go to this direction or to this direction, and to change the penetration depth of the radiation from 10 microns to 1 or 2 millimeters. And with our medical colleagues, we are thinking about different medical applications like cosmetology, when we are thinking about 10 micron penetration, or to some surgery when we go to some millimeter range. After that, we can switch several weapons. No, it's just we have one experiment, but do we have time, more time or not? No, just switch this. Instead of conclusion, do you know this person? This is Artur Shavlov from Stanford University. He got a Nobel Prize in Physics in 1981, and he told to his students, the next slide, never measure anything but frequency, of course, frequency of the laser radiation, and I hope to you to never measure anything but frequency, and that's it.